the eutectic reaction, the liquid iron, that is this liquid iron, this is the liquid portion what I said you, this is the liquidous line. This liquid iron starts solidifying into two different solid solutions. Very important thing, the liquid iron does not transforming into the one solid solution. At 1130 degrees centigrade of 4.3% carbon, which transforms into two solid solutions. This reaction is called eutectic reaction. This reaction takes place when liquid alloy containing 4.3% carbon transforms into austenite and cementite at 1130 degrees centigrade. I have shown here is 1148, it is the range in which the transformation taking place. The product of eutectic transformation is called, that is the product what I said you, liquid iron is transformed into two solid solutions, austenite and cementite. This put together it is called ledubarite. It is a mixture of austenite and cementite. You call it as a ledubarite. Now we will see what is eutectoid reaction, when it takes place. Eutectoid reaction takes place at 0.83% carbon and 723 degrees centigrade. The austenite, that is the gamma iron, transforms into ferrite and cementite. In eutectic reaction what happened? The liquid iron transforms into austenite and cementite. The liquid is transformed into two solid solutions, whereas eutectoid you see the change, eutectic liquid to two solid solutions, whereas in eutectoid one solid solution to another two kinds of solid solutions. Here it is already we have the solid solution, that is austenite, that is split into two another solid solutions, that is ferrite and cementite. This happens at the lower critical temperature, that is A1 or A123, that is at 723 isotherm line in the iron carbon diagram, and the respective carbon percentage is 0.83. This combination, this ferrite and cementite combination is called perlite. The product of eutectoid transformation, that is transformation, is called perlite. I have shown double arrow, that is on cooling it transforms ferrite and cementite, on heating the ferrite and cementite transforms as austenite. This perlite contains 88.5% ferrite and 11.5% cementite. This is the reaction. This is upper critical temperature and this is upper critical temperature, and this is where the upper critical temperature and lower critical temperature becomes a single point where this eutectoid transformation is taking place. So we will go to the next. Steels having up to 0.83% carbon are called hypoeutectoid steels, whereas steels having carbon percentage from 0.83 to 2% are called hypereutectoid steels, because at 0.83 what we have discussed, eutectoid reaction is taking place. So up to 0.83 the steels are called eutectoid steels. At 0.83 it is pure eutectoid steels. Up to 0.83 it is hypoeutectoid steels. At 0.83 it is eutectoid steels. From 0.83 to 2 it is hypereutectoid steels. Whereas what we have discussed at 4.3% carbon, eutectic reaction is taking place. So iron having from 2 to 4.3 are called hypoeutectic. At 4.3 it is eutectic. From 4.3 to 6.67 it is called hypereutectic. I will summarize it. 0 to 0.83 hypoeutectoid, at 0.83 eutectoid, 0.83 to 2 hypereutectoid, 2 to 4.3 hypoeutectic, at 4.3 eutectic, from 4.3 to 6.67 hypereutectic steels. Now we will see the composition of phases. The percentages of phases that exist in steels with various percentages of carbon can be calculated by applying lever rule. We will see the lever rule, that is we will draw a isotherm line by taking one fulcrum. This is the respective carbon percentage at phase A, the reference fulcrum the respective carbon percentage, and this is another phase, the respective carbon percentage here. We will take one example so that we can understand betterly. The percentage of composition of A can be calculated as length of arm of opposite side from the fulcrum divided by total length of lever arm, that is in the previous slide, yz by xy, and percentage of composition of B is xz by xy. Okay, we can see in detail by taking a problem. Let us take calculation of ferrite and cementite in hypoeutectoid steel containing 0.6% carbon. We will draw lever line or isotherm line at 723 degrees centigrade as lever line. This is a 723 degrees centigrade line, this is isotherm line in iron carbon diagram, and the percentage at which we require the 0.6% carbon. At 0.6% carbon, what is the ferrite and what is the cementite? Now let us see, at 0.025% carbon it is 100% ferrite, we know it very well. At 6.61% it is 100% cementite, but we require what is the ferrite percentage and what is the cementite percentage at 0.6% carbon. So that point is the reference point, it will become a fulcrum, and we know it is at the beginning it is 100% ferrite, the beginning is the carbon is 0.025% carbon, at the end 100% cementate, the end is 6.61% carbon. Now in order to get what is the percentage of ferrite at this point, you require to take this percentage to this percentage divided by this percentage to this percentage. Now we will see composition of ferrite and cementite. The percentage composition of ferrite is 6.67 minus 0.6 divided by 6.67 minus 0.025, that is 0.9134, that is 91.34 percentage of ferrite is there, whereas percentage composition of cementite 0.62 0.025 divided by 6.67 minus 0.025, the cementite is 0.0865 percentage, that is the ferrite here it is 91.6% carbon, the ferrite is 91 percentage, and whereas cementite is the 100 minus 91, that is 8.65 percentage. And this is another iron carbon diagram, it is a reference I have shown you. This is the determination of hardening temperature at 0.6% carbon steel. These are the reference diagrams I am showing you. This is a pure structure I have discussed, the respective detailed microstructures here we have given. This is the clear structure, that is A is a pure ferrite, that is pure iron at 100 magnification, and whereas this B, the perlite at 0.8% carbon, 100% perlite, and this is the C, this is the martensite, that is a hardened steel, quenched hardened steel, this is taken at 500 magnification. Based on this diagram we have made our discussion. Hello, we covered in our session various allotropic forms of iron, various phases, crystal structures of iron at different temperatures with varying percentage of carbon, and critical temperatures in iron carbon system, and three important phase transformations such as peritectic, eutectic, eutectoid reactions. And finally also we have seen the computation of percentages of phases at different percentage of carbon in steel and iron. Thank you. Goodbye.
Hello students, welcome to this lesson on plain carbon and alloy steels. In this lesson we are going to learn what is plain carbon steel, classification of steel, composition of various steels and their application. We will also learn about what are alloy steels along with their composition and applications. Now, let us learn what are the features of steel. Steel is most widely used engineering material. It is cheap because it is easily available and it provides a very wide range of mechanical properties from a very soft condition to a very hard condition. Steels are broadly classified into two groups, namely plain carbon steels and alloy steels. Plain carbon steels contain iron and carbon as basic elements, whereas alloy steels contain iron, carbon and one or more alloying elements like tungsten, nickel, chromium, etc. The carbon has strong influence on the properties of steel. When carbon content is very low, the steels are soft and ductile and possesses less strength. When carbon content is high, it is hard and possesses good strength. So, increase in carbon content reduces ductility and impact strength of the steel, but it increases hardness of the steel. The same thing can be observed by looking at this graph. Here percentage of carbon by weight, it is taken on the x axis, whereas tensile strength, percent elongation, Brinell hardness number are taken on y axis. By observing this graph, we can say that hardness of the steel increases gradually with the increase in carbon content. Similarly, tensile strength also increases, but percent elongation decreases with the increase in carbon content. Now, we go in detail for plain carbon steels. Let me define what a plain carbon steel is. It is defined as an alloy of iron and carbon in which carbon is less than 2%. In addition to carbon, plain carbon steels also contain some impurities like sulfur, phosphorus, silicon and manganese in minute quantities. Plain carbon steels are classified depending on the percent of carbon as low carbon steels, medium carbon steels and high carbon steels. Let us take low carbon steels first. The composition of low carbon steel is like this. They contain carbon from 0.08 to 0.3%. These steels are further divided into two groups, namely dead mild steel and mild steel. Now, we discuss about mild steel. Mild steel contains carbon from 0.15 to 0.35%. This steel possesses good tensile strength and ductility because carbon content is low. It undergoes corrosion when exposed to the atmosphere. This is a main drawback of the mild steel. Coming to the application part, these steels are used for making bolts and nuts. It is extensively used in structural works and in making axles, shafts, etc. Next, we take up medium carbon steels. The composition of medium carbon steel is like this. It contains 0.03 to 0.6% carbon, and these steels have better strength compared to low carbon steels. Typical application of these steels are rails, connecting rods, gear wheels. Then next, coming to high carbon steels, these steels contain carbon from 0.6 to 1.7%. The main advantage of high carbon steels is, with proper heat treatment, these steels attain good hardness, wear resistance along with toughness, and because of this property, these steels are widely used for making general tools, gears, tapes, dies. So far we have studied plain carbon steels. Now we study about some important alloying elements which are added to the steels. The purpose of adding these alloying elements are like this: to improve mechanical and physical properties of steel like hardness, strength, toughness, and to improve corrosion and oxidation resistance, and to improve magnetic and electrical properties. By adding alloying elements, the ability of the steel to withstand high temperature also increases. Let us look at some important alloying elements. They are nickel, chromium, tungsten, molybdenum, manganese, silicon, copper, cobalt, etc. So, before proceeding further, let me define what is alloy steel. Alloy steel may be defined as the steel which contains alloying elements in addition to iron and carbon. An alloy steel may contain one or more alloying elements. These steels have high hardness, strength and toughness compared to plain carbon steels. These steels also have good corrosion and oxidation resistance. Now we study about effect of some alloying elements on the properties of steel. First we take up nickel. Nickel increases coefficient of thermal expansion of steel. It increases tensile strength of the steel and refines its grains, so that toughness of the steel is increased. Next, chromium. Chromium increases strength, hardness, wear and corrosion resistance of the steel. Now manganese. Manganese lowers melting point of steel. It increases strength and hardness. Next, silicon. It improves magnetic permeability and electrical resistivity of steel. it also increases resistance to oxidation. Coming to tungsten, it imparts red hardness and hot strength. It inhibits grain growth. Next, molybdenum, it increases corrosion and abrasion resistance. It imparts hot strength, red hardness and toughness. Vanadium, it prevents softening of steel at elevated temperature. It promotes fine grained structure. It increases tensile strength, ductility and toughness. Now coming to cobalt, it imparts excellent magnetic properties. It also increases the red hardness of the steel. Now copper, copper increases corrosion resistance, strength and hardness, but it lowers the ductility and impact strength of the steel. Aluminum, it increases resistance to oxidation, restricts grain growth and aids nitrading. Let us see some examples of alloy steels. First one is chromium steels. These steels contain chromium from 0.5 to 13%. These steels have excellent wear and corrosion resistance. Because of presence of chromium, wear and corrosion resistance properties of the steel improve. Hence, they are used for making ball and roller bearings and surgical instruments. So next, stainless steels. These steels contain chromium and nickel as alloying elements. Example for stainless steel is 18/8 steel. That means it contains 18% chromium, 8% nickel, 0.15% carbon. Coming to the properties, these steels possess extraordinary toughness and ductility, corrosion resistance, and these steels can be rolled into strips. Hence, they are used for kitchen articles, medical and surgical instruments. So next, manganese steels. These steels contain manganese 1 to 2%, carbon 0.25 to 1%. These have high strength, toughness and resistance to abrasion. These steels are used for making gears, shafts, axles, dies, cams, taps and reamers. Next, hot filled manganese steel. This is a special case of manganese steel. These steel contain manganese 10 to 16%, carbon 1 to 1.1%, silicon 0.25 to 1%, phosphorus 0.1% and sulfur 0.05%. These steels possess high toughness and abrasion resistance. These are developed for making railway rails and these also used for making helmets, crushing machinery parts, crankshafts, etc. Now coming to high speed steels. These steels contain tungsten, chromium, vanadium, cobalt and molybdenum as alloying elements. Example for high speed steel is 1841 HSS steel, which contains 18% tungsten, 4% chromium, 1% vanadium, 0.8% carbon. These tools are used for high speed cutting tools because they retain their hardness at high temperatures up to 600 degree centigrade. Let us recollect what we have discussed now. We have learned that plain carbon steels are iron carbon alloys with carbon up to 2%. We have classified plain carbon steels as low, medium and high carbon steels. We learned that properties of steel greatly depend upon the amount of carbon present in it. We have seen that hardness and strength of steel increases with increase in carbon content, but at the same time ductility of steel decreases. We also learnt about alloy steels. Now we know that alloy steels contain additional elements like chromium, nickel, tungsten, etc. to give the steel the desired properties. We have seen examples of alloy steels like nickel steels, stainless steels, high speed steels, manganese steels, etc. With this we come to end of this topic. I hope you understood this lesson. Have a nice time. Goodbye.
Further clarification, contact the Additional Secretary, State Board of Technical Education and Training, 7th floor, BRKR Bhavan, Tank Bund Road, Hyderabad 500063. Fax 040 322 0546.